Hello friends, this is a re-record of today's lecture because the audio wasn't actually recording when we were in class together. So last time we were talking about the origin of spin-spin splitting. We talked about where doublets come from, we talked about where triplets come from. Recall that for a triplet, that's the pattern we observe when the blue proton, which is our proton of interest or our absorbing proton, is adjacent to two identical protons, A and B. And the triplet happens because proton A can either be aligned with or against the external magnetic field in about a 50-50 ratio. Same thing for proton B, and so in terms of what the blue proton, our absorbing proton, experiences, it can experience the external magnetic field plus the environment where both A and B are aligned with the magnetic field. It can experience the environment where A is aligned with or B is aligned against, or where A is aligned against and B is aligned with. Both of those environments feel the same to our blue absorbing proton. And then it can also experience an environment where both A and B are aligned against the magnetic field. And then based on these 50-50 ratios, you can predict that these three situations should be present in basically a 25 to 50 to 25 or a 1 to 2 to 1 ratio. And that's where we get this 1 to 2 to 1 triplet peak. And when we say triplet, that intensity of 1 to 2 to 1 is implied in the term triplet. So a triplet is not just three lines, it is three lines that are present in a 1 to 2 to 1 ratio. And we pointed out that two protons that split each other's NMR signals are said to be coupled to each other. So the A and B protons are coupled to the blue proton, and the blue proton is coupled to the A and B protons. And the coupling constant refers to the spacing. The coupling constant J refers to the spacing between peaks in a triplet or a doublet pattern. And that coupling constant should be equal for coupled protons. So we would expect the coupling constant observed for the blue peak triplet should be the same as the coupling constant observed for the doublet peak we would get for protons A and B because they're adjacent to the blue proton. Okay, so simple rules for splitting are that identical homotopic or enantiotopic protons do not split each other. That means that A and B do not split each other. Second, that if our absorbing proton is the blue proton here, a set of n adjacent protons, where the n adjacent protons are identical to each other, will split the signal of the absorbing proton into n plus 1 peaks with relative peak areas that basically follow the ratios predicted by Pascal's triangle. So for a doublet, we expect a 1 to 1 ratio between peaks. For a triplet, we expect a 1 to 2 to 1 ratio between peaks. For a quartet, we expect a 1 to 3 to 3 to 1 ratio between peaks, and so on. And we call the peaks sort of these names, quintet, sextet, septet, for 5, 6, 7 line peaks that come from having 4, 5, and 6 adjacent protons respectively. Peak ratios is indicated here. One thing I didn't necessarily point out in class, but I will here, is that as peak structure becomes more complicated, sometimes we don't observe all the lines in the peak because these outer peaks can actually be quite small, and some of the peaks are not clearly visible. When this happens, we call this a cluster of peaks in this range to be a multiplet, which is sort of hedging on exactly how many lines are present in the sample. And when you call something a multiplet, all you really know is that there are a lot of adjacent protons. So let's look at some common splitting patterns. Before doing that, I will point out the last simple rule for splitting, which is that We observe splitting for peaks that we observe splitting between non-identical protons that are on the same carbon or are on adjacent carbons. Protons that are either 2 or 3 bonds away from each other. Splitting beyond 3 bonds can sometimes be observed, but most commonly it's between protons that are either 2 or 3 bonds away from each other. So here are some splitting patterns that we can observe. Let's zoom in on the first. The squiggly lines here mean that the 2 carbons are attached to other things that are not protons. We're focusing in on what the red and the blue protons should experience. So if the red proton is only adjacent to 1 and only 1 proton, we expect to see a doublet for the red proton. For the blue proton, we similarly expect to see only a doublet. That's the pattern that's here. If we were to measure the splitting between the peaks, the coupling constant, it would be the same for the set of peaks that represents red proton, and it would be the same splitting pattern, same coupling constant for the doublet that represents the blue proton. We're not really saying what the chemical shifts of these protons are. They might not be. There's NMR signals might not be immediately adjacent to each other, but we expect each to be a doublet. Similarly, let's look at proton red proton, which is a single proton that's adjacent to 2 blue protons. We would expect for the red proton to see a triplet, a 1 to 2 to 1 triplet, and we would expect for the blue protons to see a doublet, a 1 to 1 doublet, because the blue protons are adjacent to only one other proton. And that's what we've got here, a 1 to 2 to 1 triplet and a 1 to 1 doublet. I will point out that in addition to the splitting pattern, the area under the peak will provide useful information. For example, we would see that the NMR signal representing the red proton should integrate for just 1 proton versus the peak representing the blue protons should integrate for 2 protons, or the ratio between the peak areas of the triplet and the doublet should be 1 to 2. How about 2 CH2 groups adjacent to each other and to no other protons? We would expect to see a triplet for the red protons and a triplet for the blue protons. We would expect these 2 triplets to integrate for the same number of protons, or a 1 to 1 ratio of peak areas, because the signal for the red protons comes from 2 protons, and the signal for the blue protons also comes from 2 protons. For an ethyl group, that is a CH2 group adjacent to a CH3 group, where the CH2 group is not adjacent to any other proton, we expect to see a quartet for the red protons and a triplet for the blue protons, because the red protons are adjacent to 3, whereas the blue protons are adjacent to only 2. We would expect the ratio of peak areas to be 2 to 3, corresponding to the number of protons represented by each peak. Again, a quartet for the CH2 group, signifying that it's adjacent to 3 protons, and a triplet for the CH3 group, signifying that it's adjacent to 2 protons. And then finally, a CH proton adjacent to a methyl group. We expect the red proton to be a quartet and the blue proton signal to be a doublet. And we expect the ratio of peak areas to be 1 to 3. Okay, so let's test you on this. What would you expect the peak splitting pattern to be for this molecule? In class, some of you were inclined to say triplet because you saw that this CH2 group is adjacent to this CH2 group. However, all the protons are identical in this molecule. So we should see only one peak, only one NMR signal. There should be no splitting because identical protons do not split, so we expect to see just a singlet. All right, in this ketone, I've told you that there are 3 different kinds of protons. Let's predict the splitting that we should observe for each. The pink protons are adjacent or within 3 bonds or less of no other protons. There are no other protons within 3 bonds or less, so we expect to see a singlet. For protons B, the blue protons, we expect to see a quartet. They are adjacent to 3 other protons in the methyl protons. So we expect to see a quartet. For HC, we expect to see a triplet because the orange protons are adjacent to 2 blue protons. All right, let's move on to this example. Here is where we expect to see triplets, both for the pink protons and for the orange protons. How about for these blue and pink protons attached to an alkene? These 2 protons are diastereotopic. They are different from each other, so we expect them to split each other. Proton A is adjacent to 1 other proton, so we expect proton A to be a doublet, and we also expect proton B to be a doublet. And then lastly, for this molecule, we expect to see a doublet for this CH2 group and a triplet for this CH group. All right, now let's deal with some more complicated splitting patterns. Notice that in each of the examples that we've done so far, a given proton of interest has only been adjacent to 1 set of protons. For example, the CH2 group protons are only adjacent to the methyl protons. There's no protons on the other side. What if there were? How will that complicate the splitting pattern? If the absorbing proton has adjacent protons on more than 1 carbon, what happens can be simple or complicated. Let's deal with the simplest case first. So let's suppose the absorbing proton has adjacent protons on more than 1 carbon, but those adjacent protons are identical to each other. Such is the case in this molecule 2-bromopropane. Blue proton B is adjacent to 2 identical methyl groups. When that happens, we can just use the same expectations that we'd used previously for the simplest case. That is, we can say the blue proton is adjacent to 6 identical protons. We'll use the n+1 rule, which tells me that I should see a 7-line pattern, a septet, with intensities more or less predicted by Pascal's triangle. So a 1 to 6 to 15 to 20 to 15 to 6 to 1 ratio of peaks. This is the NMR spectrum of 2-bromopropane, and indeed, for the blue proton, we do see a 7-line pattern with approximately that peak height / areas, relative peak areas in the ratio sort of predicted by Pascal's triangle. So we do see a septet there. In other words, if a proton's identical to 2 sets of identical protons, you just follow the usual n+1 rule for what you would expect. In addition, these adjacent methyl groups, they're each adjacent to only 1 other proton. We expect them to be present as a doublet. That's what we see. If we integrated the peak areas, we would expect to see a 1 to 6 ratio between those peaks. All right, so let's deal with a more complicated case. What if those adjacent protons are actually not equivalent to each other? In such cases, the outcome is going to depend on the coupling constant between our absorbing proton of interest and the two different kinds of adjacent protons. So let's deal with the simplest case, and that is for flexible alkyl chains where coupling constants between adjacent carbons are similar. So here is one bromopropane, and we'll be talking about the blue protons, but that are labeled B. We'll be considering what we will observe for those. The blue protons are adjacent to the 3 protons of methyl group A that are labeled in pink, and the 2 protons of this CH2 group C, which is labeled in orange. Now we're going to, because there's free rotation around these carbon-carbon bonds, the alkyl chain is flexible, we will assume that the coupling constant between A and B is similar to the coupling constant between B and C. That the influence of the A protons on B is similar to the influence of the C protons on B. In such cases, even though A and C protons are not equivalent to each other, we can just use the same rule that we've used previously, that the signal for B, because B is adjacent to 5 protons, and that those 2 sets of protons have similar coupling constants with B, we should expect B to be split into a sextet with peak height / areas, relative peak area ratios within that sextet pattern determined mostly by Pascal's triangle. So this is in fact what we observe. Here is the NMR spectrum of one bromopropane, and we see for the blue protons B a sextet pattern, a 6-line pattern, roughly 1 to 5 to 10 to 10 to 5 to 1 pattern. If we were to measure the relative areas of the 3 sets of peaks, we would see that a 2 to 2 to 3 ratio. It makes sense that the orange protons should be a triplet because they're adjacent to 2 protons. It similarly makes sense that the pink protons should be split into a triplet because they're adjacent to only 2 protons. It makes sense that the peak for the orange protons should integrate for 2, whereas the peak for the pink protons should integrate for 3. And again, for the B protons, the reason we see a 6-line pattern is because the coupling constant between A and B is pretty close to the coupling constant for C. Finally, chemical shift here makes a lot of sense. We expect the HC protons to be de-shielded relative to the others because the C protons are closest to the bromo group. And then we expect chemical shift beyond that to basically track with distance from the bromo group, where the blue protons B are de-shielded relative to the pink protons A. But the blue protons B do not show up at as high chemical shift as the orange protons C. Okay, so case 2 is more complicated. This is the case where the adjacent carbons, the protons adjacent to our absorbing proton of interest are not equal to each other, and the coupling constants are not equal to each other. Before we talk about that specific case, I need to illustrate to you some situations in which coupling constants for different sets of adjacent protons can be dramatically different. And the classic example of when this is true is for protons on the sp2 hybridized carbons of alkenes, on vinyl carbons. In our subsequent discussion, I'm going to call these vinyl protons. So, for protons on an alkene, 2 diastereotopic protons on the same carbon of an alkene often have a coupling constant in the range of 1 to 2 hertz. By the way, protons attached to the same vinyl carbon are called geminal protons, and so we'll refer to the geminal coupling constant of being between 1 and 2 hertz. Protons that are on adjacent vinyl carbons but are cis to each other generally have coupling constants in the range of 5 to 10 hertz, whereas protons that are on adjacent vinyl carbons but are trans to each other generally have much larger coupling constants in the range of 15 to 18 hertz. I wouldn't expect you to know these numbers or have them memorized, but I would expect you to know that the trans coupling constant is greater than the cis coupling constant, which is greater than the geminal coupling constant. So here are a couple examples of NMR spectra for or NMR signals for vinyl protons in two different stereoisomers, and you can distinguish between those stereoisomers by measuring the coupling constant. So for Z3-chloropropenoic acid, we've got two different kinds of vinyl protons, A and B. We each expect them to be doublets. They are cis to each other. We expect the coupling constant to be in the range of 5 to 10 hertz. In this particular case, it's about 8 hertz. For the trans stereoisomer, these vinyl protons that are trans to each other, we expect the coupling constant to be larger for trans than for cis, and indeed we observe the spacing between the doublet peaks to be around 14 hertz. By observing that we see a larger coupling constant here than here would tell me that this is the trans isomer and this is the cis isomer. So again, coupling constants for trans are greater than for cis, and cis is greater than for geminal. So let's show you how this works with a complicated example of this ester. So you have 1, 2, 3, 4 different kinds of protons in this molecule. The methyl group would be a singlet. We'll call that HA. Then the remaining protons, B, C, and D, are all vinyl protons. B and C are diastereotopic. They are not identical. And D is also its own thing. B is geminal to C. B and C are not identical, so we expect there to be geminal coupling between B and C. And in this case, we wouldn't have predicted this, but I'll tell you the outcome is 1.2 hertz. We would have predicted something in the range of 0 to 3 hertz. For this particular molecule, the geminal coupling constant is 1.2 hertz. However, B is also trans to D, and that trans coupling constant is around 14 hertz. C is geminal to B, so we expect the same 1.2 hertz coupling constant for proton C. We also expect a cis coupling constant between C and D, which should be around 6.5 hertz, or at least that's what it is measured in this case. So for each of these peaks, let's see what we expect. Let's start by considering proton B. Proton B should be split by proton D into a doublet pattern where the peak spacing is 14 hertz, but should also be split by proton C into a doublet pattern where the peak spacing is 1.2 hertz. Here is how that works out for proton B. This line represents the chemical shift for proton B if we could turn off coupling with the adjacent protons. All right, so let's then turn on the splitting with proton D, that large trans coupling, split by 14 hertz into a doublet. And then after that, let's turn on the splitting with geminal proton C, a splitting pattern of a doublet of 1.2 hertz. each of those peaks from the 14 hertz doublet gets split into its own 1.2 hertz doublet. What we see is a pattern that's called a doublet of doublets. And it's a 1 to 1 to 1 to 1 pattern. The splitting between the smallest splitting is that JBC splitting. And then if we measure the splitting between corresponding peaks in those individual doublets, that's the 14 hertz spacing. So we call this a doublet of doublets because the line for proton B gets split first into a 14 hertz doublet, and then those individual lines get split into their own doublets. Okay. Now let's consider the pattern for proton D. Proton D has a trans coupling constant with B and a cis coupling constant with C. So we expect the line for proton D to be split into a 14 hertz doublet, and then for each of those lines in the 14 hertz doublet to be split into a 6.5 hertz doublet by proton C. And that's exactly what we see, where this spacing between the smaller spacing is the 6.5 hertz spacing, and then the spacing between corresponding peaks in those smaller doublets is the 14 hertz spacing. Now in class, it was asked, how do you know whether a pattern like this is a doublet of doublets or whether it's just two individual doublets? And the answer is you'll look for spacing between the two doublets in the range of 15 to 18 hertz. The other thing you can do is look for relative peak areas. For example, for this molecule where I know that I've also got a 3-proton singlet, if I were to integrate both of these doublets, I would see a peak area corresponding to 1 proton. If I integrated only one of them, I would see peak area corresponding to half a proton, which wouldn't really make sense. I can't have non-integral values of protons. So sometimes peak area will tell you whether you're looking at two isolated doublets or in reality a doublet of doublet pattern. Now let's look at the blue proton C, which should be split into a 6 hertz doublet and then into a 1.2 hertz doublet. Again, we see the line for proton C split by the coupling constant with D into a 7 hertz doublet roughly, and then each of those lines split into a 1-to-1 doublet pattern of around 1.2 hertz. Okay, and you'll notice that the 1-to-1 to 1-to-1 pattern of doublets, there's sometimes some deviation for this. Some amount of leaning is allowed. This is a leaning doublet, but the doublets will usually lean in the same direction. So this is a doublet of doublets pattern. Now let's see if we've got it. Let's predict the splitting pattern for this molecule. Of course, for proton A, it's easy. Proton A is adjacent to proton B and only B, so we expect proton A to be a doublet. And because I've said that the coupling constant between A and B, which are trans to each other, is around 13.1 hertz, we expect that to be the spacing for the doublet for proton A. Similarly, for protons C are adjacent to proton B. We expect proton C to also be a doublet. That would integrate for 2 protons. Now let's deal with proton B. Proton B is adjacent to proton A and should be split into a doublet by proton A of about 13 hertz. And then each peak in that 13 hertz doublet should be split into a triplet with spacing of around 7 hertz. So let's sort of predict how that would happen. Here is the line for proton B if we were able to turn off the coupling constant between A and B and the coupling constant between A and C. And just for fun, let's suppose this spacing let's suppose this spacing is around 13.1 hertz. So if we turn on the coupling between A and B of 13.1 hertz, we expect to split the peak for proton B into a two-line one-to-one doublet where the spacing there corresponds to the JAB coupling constant of 13.1 hertz. Okay, and then at that point, each of those individual lines should get split into a 7.2 hertz triplet. Let's see, this spacing here is around 7.2 hertz. We're trying to stay to scale. So I'll use gray for that next coupling constant. Let's turn on the coupling constant between B and C, which equals 7.2 hertz. Each of those individual doublets should be split into a 1 to 2 to 1 triplet, where the spacing between triplet peaks should be 7 hertz, like that. And then maybe I'll use a different color for the other one, and you will see this sometimes. Depending on the coupling constants, sometimes the peaks can actually overlap with each other. So this distance here is 7.2 hertz, whereas this distance here is also 7.2 hertz. You can see the middle peaks in this pattern, the peak from the blue triplet and the first peak from the blue triplet and the last peak from the gray triplet overlap with each other and sort of flank each other in that way. We would call this pattern a doublet of triplets. And it is a 6-line pattern. Now your text points out something called the n+1 times m+1 rule, which applies when coupling constants for adjacent protons are not equal to each other. In this case, n is the number of protons A and m is the number of protons C. And your text points out that you should expect to see if here n equals 1 and m equals 2, then n+1 times m+1 is 6. We expect to see a 6-line pattern. I don't usually spend a lot of time worrying about the n+1 and m+1 rule. I simply go through it as we have. I consider turning on the coupling constant with A to make a 13 hertz doublet, and then turning on the coupling constant with C to make each of those peaks from the 13 hertz doublet into its own triplet, its own 7 hertz triplet. We will abbreviate that doublet of triplets with the letters D and T. Why not a triplet of doublets? You could, if you wanted. Usually we start with whichever coupling constant was larger. All right, let's do this again for this slightly more complicated molecule. I'm sorry, my notes from class are still here. Sorry about not actually capturing the audio from class. So here I've shown you a molecule with 1, 2, 3, 4, 5 different protons. And the purple protons E, the methyl group that are not adjacent to any other kind of proton, should be a singlet. I've also in red illustrated what you should use to predict the splitting patterns in terms of coupling constants. So we'll say that the coupling constant between protons A and B is around 6 Hertz. Coupling constant between protons B and C, vinyl protons B and C that are trans to each other, we're going to estimate around 14 Hertz. And then coupling constants between C and D, we're going to estimate to be around 6 Hertz. Of course, for green protons C, we expect to see simply a doublet, about a 6 Hertz doublet. And similarly, for pink protons A, we expect to see a doublet because pink protons A are adjacent to only one kind of proton. For proton B, what should we expect? Well, let's imagine the line for proton B, then let's turn on the coupling constants with the adjacent protons one by one, starting with the biggest. So let's turn on the 14 Hertz coupling constant with proton C. We expect to see a doublet for proton C of about 14 Hertz. And that doublet should be split into a 6 Hertz quartet by the 3 adjacent protons A. So we expect to see a doublet of quartets. Now, if you use the n+1 times m+1 rule, you would expect to see an 8-line pattern. But the doublet of quartets, or DQ pattern, tells you that there will be 8 lines there. Okay, how about for proton C? Proton C, you expect to again see a 14 Hertz doublet for the coupling constant between B and C, split into a 6 Hertz triplet. So we expect to see a doublet of triplets, or DT pattern, for the orange proton C. As I mentioned before, sometimes when you have this many lines, the patterns can be difficult to interpret, but it's important to at least be able to have an idea of what to expect. All right, so now we're just about ready to solve some unknown structures. Before we get there, I need to deal with just a few minor issues that aren't necessarily worth memorizing, but will be useful for you as you interpret NMR spectra. First is for protons on heteroatoms like O and N, for alcohol and amino protons, not necessarily for amides. These protons can have widely variable chemical shifts because they are frequently involved in intermolecular hydrogen bonds, which can lead to varying environments for OH and NH protons. Sometimes the peaks for OH and NH protons are not very sharp. Sometimes they are broadened out due to hydrogen bonding and rapid proton exchange. And sometimes these OH and NH protons do not split, nor are split by adjacent protons. So as an example, here is an NMR spectrum for ethanol. You see the expected quartet for protons B, which are adjacent. Okay, sorry, let me back up. For ethanol, for the methyl group, you would predict that the methyl group should be a triplet, and it is, and it integrates for 3 protons. But for the CH2 group, you might expect to see not a quartet for being adjacent to 3 protons, but perhaps a pentet or a 5-line pattern because the B proton is adjacent to 4 protons. However, because this proton C is on an oxygen and is involved in rapid exchange with other molecules, we don't see splitting between C and B. So proton C shows up as a singlet and the B protons show up as a quartet. How would you know, therefore, that that OH proton was there? Well, you would get it from the molecular formula, you could get it from the IR information, but you should not expect to see splitting between an OH proton and the adjacent protons. As an added complication, something that I mentioned in class that your text doesn't say, but you may experience in the 353 lab, is that depending on what your solvent is for the NMR experiment, protons on heteroatoms can actually exchange with deuterium atoms in the solvent and disappear from the NMR spectrum. Okay, another sort of minor issue is that there are plenty of molecules in organic chemistry where there is some conformational equilibrium happening. So, for example, with cyclohexane rings, you would expect the axial environment for proton A to be different from the equatorial environment. Nevertheless, if you take an NMR spectrum of cyclohexane, you only see one proton here. Or rather, you only see one signal for proton A. And that is because the exchange between these two conformations is so rapid on the NMR time scale that you don't see two different environments, you just see an average environment for one signal. So for protons in cyclohexanes, we don't expect, because the axial and equatorial environments are rapidly interconverting, we don't expect to see two different environments. We expect to see an average environment. Finally, for monosubstituted benzenes, that is a benzene ring that's attached to one non-hydrogen thing, we expect to see 3 different signals, 3 different kinds of protons labeled in pink, blue, and orange respectively. And we expect there to be coupling constants between A and B and between B and C. However, the specific chemical shifts and coupling constants of these A, B, and C protons depend highly on the identity of the group that's attached to the benzene ring. For example, if the group is alkyl or a ketone or an ether, you can see different chemical shifts and different splitting patterns. You can analyze these, but we won't in 351, in part because you don't need to. In either of these peaks, if you did the peak integration, they would integrate for 5 protons, and that would already tell you everything you needed to know about the molecule, that the molecule had a benzene ring attached to one non-hydrogen thing. So we won't be analyzing the splitting patterns of monosubstituted benzenes in this class. All right, with that, we're ready to identify an unknown. We did this in class. I've got my notes from our in-class discussion already on the structure, so the solution's already there. Sorry about that. The molecule has a formula C4H8O2, and the IR tells you have a carbonyl. I'm not showing you the IR data. Sometimes in problems in the text, it will simply tell you the conclusion you're supposed to expect from the IR data, or that you would have gotten from analyzing the IR data. The first thing I like to do when solving the structure of an unknown is to calculate the degrees of unsaturation or the double bond equivalence based on the molecular formula. So that's 2 times the number of carbons plus 2 minus the number of hydrogens divided by 2. I get 1 double bond equivalent, that is 1 pi bond or ring. And actually, my IR data already tell me what that double bond equivalent has to be. It has to be a carbonyl. So one of the things I like to do is just draw the parts of the molecule that I have evidence for based on the data. Right now I know I have a carbonyl, and it's attached to 2 other things because that's what the Lewis structure of a carbonyl would tell me. Based on the molecular formula, I also know I have another oxygen. I don't know what it's attached to, but I don't think it's attached to other protons because my IR would have had to tell me if it was an OH group. Now let's look at my 3 peaks. They've already given you peak areas, relative peak areas, and then you can see the splitting patterns for peaks A, B, and C. Peak A is a triplet, peak B is a quartet, and peak C is a singlet. A singlet that integrates for 3 protons would need to be a CH3 group, where what's attached over here doesn't have protons on it. I can think of 2 possibilities given what I already know about my structure. I can think of a CH3 group attached to an oxygen, or I could imagine a CH3 group attached to a carbonyl. Now it turns out only one of these possibilities is consistent with my data. If I went back to look at the NMR table in my text or in my notes, I would see that for protons adjacent to oxygens, I would predict chemical shift to be from around 3 to 4 ppm. But for protons adjacent to carbonyls, I would predict chemical shift to be in the range of 1.5 to 2.5 ppm. Of course, the singlet peak that we're talking about here has a chemical shift of around 3.6, 3.7 ppm. That's consistent with being adjacent to an oxygen, but not with being adjacent to a carbonyl. So, as I'm starting to put together some pieces, one of the pieces I want to consider now is a methoxy group, that is a methyl group attached to an oxygen. Okay, how about the other peaks? Well, the B peak looks like a CH2 group that is adjacent to a CH3 group, where what's attached on the other side of that CH2 group doesn't have protons. And you can start to see that I will get complementary information from the spectra. For example, the fact that this B peak was 2 protons but a quartet tells me it's a CH2 group adjacent to a methyl group. But over here, I see a 3 proton peak that's a triplet telling me that this is a methyl group adjacent to a CH2 group. Complementary information. So another piece I've now assembled is an ethyl group, a CH2-CH3 group, where what the CH2 group is attached to is not a proton. Okay, so it turns out the pieces I've got left are carbonyl, methoxy, ethyl, and if I count up the atoms, I've accounted for all the atoms in my formula. There's only one way to put those pieces together, and that is to be like this. Now, when we come back next time, I'll show you how to check your answer to make sure that your answer for the structure of the molecule adequately accounts for all of the data. We'll do a lot of other examples for solving the structures of unknowns. And then we'll also introduce really briefly carbon-13 NMR, which is a complementary technique. It's not emphasized heavily in 351 or 352, but it is used by organic chemists, and so I want you to be aware of it. You will also likely encounter it when you take the organic 353 lab, so I want you to be prepared and understand a little bit about C13 NMR. And with that, we'll see you next time.